So predicting the anode and cathode half reactions in electrolysis. So predictions of half reactions follow the same process that we use for voltaic cells. So it's still going to be that the strongest oxidizing agent and the strongest reducing agent react. The thing that we're expecting that's going to be different is that the strongest oxidizing agent is below the strongest reducing agent. So this is non-spontaneous. So we have to give it electricity for that reaction to go forward. So in the electrolysis of water, we can do that by carrying out the reaction where we've got just water, ions, and inert electrodes. So I have a video that shows the electrolysis of water, and we used sodium nitrate. Here it's suggesting potassium nitrate. You want to make sure that your strongest oxidizing agent is going to be so the GrOA at the cathode is going to be water, and that the LeO-Ra at the anode is also water. So water is both my oxidizing agent and my reducing agent. So if I had the potassium ions, nitrate ions, water, and then I had like platinum electrodes. The platinum electrodes are inert. Water is an oxidizing agent, a reducing agent. The potassium is an oxidizing agent, but it's terrible. So my strongest oxidizing agent and strongest reducing agent are going to be water. And so I'm going to produce these two chemicals at the anode and at the cathode and the anode. So we've got a video that shows that. So please go and reference that video. It'll try to explain that. But essentially, we're going to have a platinum electrode, we're going to have water, and we're going to have a platinum electrode. Now, in the water, I'm going to have sodium ions and nitrate ions, and that's fine. You can include those if you want. But because water is my strongest oxidizing agent and reducing agent, I'm going to use those two entities to react. And this is a disproportionation reaction. That was mentioned earlier. And essentially what happens is, because I've got potassium ion here, and I've got water here, and I've got water here, my strongest oxidizing agent is here, strongest reducing agent is here. This is going to go this way, and this is going to go this way, and that's the reaction that's going to occur. So that's the electrolysis of water. Now, if we did electrolysis and it was always in an aqueous environment, we start to run into a problem. Water is always going to be an entity in an aqueous environment. But how am I going to purify chlorine or sodium? So if I look here, if I wanted to purify the sodium, so if I wanted that sodium ion to become sodium solid, my problem is if it's in water, water will always react instead of it. And if I wanted to purify chlorine from this, the water is a stronger reducing agent. Now, this is going to have something called the chlor-alkali effect that I'll explain in a moment, but definitely we cannot at all purify sodium solid as long as there's water. So a way around that is to do reactions in a molten state. So sodium chloride solid is going to stay as a solid crystalline structure. If it was aqueous, if I dissolve it in water, it becomes sodium ions and chloride ions. But this implies that there are waters still there, and that again gets in the way of purifying my sodium. I can get rid of the water though, and we've never really looked at this before, but essentially, if I take an ionic compound and liquefy it, it becomes liquid ions. And if I just heat it up until the salt melts, I no longer have water as a possible reactant. And so I can have the sodium ion becomes sodium, and chloride ions become chlorine gas because there is no water to react. It's just the liquid. And so here we're going to have these two entities are possible because we've liquefied the salt instead of dissolving it. Now, I was saying that there's the chlor-alkali effect, and this is a must-know for the Chemistry 30 curriculum. Essentially, if we look at the data booklet and we focused up here, if I had as my entities, I had chloride ion, AQ, and water, liquid. If those were my two entities that were reducing agents, you're going to see that my chloride is here and my water is here. And if I have chloride and water, they're here. So obviously, my strongest reducing agent is going to be water. It's listed further down. It's a stronger reducing agent. But there's this weird effect that is an anomaly, so it's not what we expect. If I have chloride ions and I react them with enough voltage to be able to supply to make this happen, I will get chlorine gas produced instead of the oxygen gas here. And so when people take a sodium chloride solution will undergo this set of reactions instead. So I'm still going to have water reacting as my strongest oxidizing agent. That's on the lower left-hand column of the redox table. But chlorides are going to become chlorine gas. And this is actually how we can collect chlorine gas on an industrial scale, and it's fairly cheap. So when we did this electrolysis here, you'll notice we used sodium nitrate or potassium nitrate so that I could make my oxygen and hydrogen just from the water. Well, if I had instead used sodium chloride solution, I'd have had sodium ion, chloride ion, water. This is an oxidizing agent and a reducing agent. This is a terrible oxidizing agent, and this is a reducing agent. This is the strongest reducing agent and the strongest oxidizing agent, but because of the chlor-alkali effect, what ends up happening is that this will react instead, and that's an anomaly. It's not what we expect. The chlorides become chlorine gas, and we produce chlorine gas. When I do this demonstration in class, and it doesn't really translate well to videos, you can smell the chlorine gas being given off. It smells like a swimming pool. So another very common electrolytic reaction that you need to know is the aluminum purification. And so aluminum is an interesting chemical because it's very light and it has the aluminum itself doesn't have a high melting point, but aluminum oxide, which is what you get in nature, has an extremely high melting point. And so you can't liquefy it. If I wanted to liquefy aluminum oxide so that it becomes aluminum ions and oxide ions, to liquefy that, I need to heat it up so much that it can't be held in anything. So for the longest time, aluminum was an extremely expensive element, but there were two different scientists, one in France and one in America, so Hall and Haru, and they both kind of discovered this at the same time. If they dissolve the aluminum oxide instead of trying to melt it or dissolve it in something else, if they dissolve it in a chemical called cryolite, CRY, you can get CRY, CRY, and cryolite is this weird chemical here. This will become liquid, and you can dissolve the aluminum and the oxides in the cryolite, and then the strongest oxidizing agent is aluminum, strongest reducing agent is oxygen, and you're able to refine aluminum and you'll also get some oxygen. They really want the aluminum, and this dropped the price of making aluminum to the point where your aluminum can is worth 5 cents. It used to be worth more than gold because it was so difficult to refine. I'm going to talk about electroplating in another video because this is getting a little on the long side, but electroplating is super, super important.